Okay, here's my next project. It's called ourLora. It's going to be out there as ourLora.com. It's going to be an IoT based monitoring project that uses LoRaWAN connectivity. So I'm going to be using a pycom low-pi 4 board, which can communicate through LoRa and LoRaWAN. So you can see the board there. And then I'm going to be using that board as a node endpoint to monitor the status of my boat, which is going to be up in its dock miles away. So this board, it's going to be communicating using the LoRa radio technology, which is a low power, long range radio technology, especially for IoT. And that's going to be talking first to a LoRa and a LoRaWAN gateway. I'm going to be using a gateway that comes from the Things network, and this is it. So this LoRaWAN gateway then talks to the Things network backend servers, which will take the data, do some transformation to that data, and then has various integrations, and I'll be using the HTTP integration to send that data received from the gateway onto a Firebase cloud function. Now, Firebase is part of Google's cloud services. So that cloud function will receive the data as a post from the TTN network. It may do some more transformation and then adds the data as a document into the Firestore database. Again, part of the Firebase cloud system. Then finally I'll write a Angular UI front end to look at the data in that Firestore database and actually be able to see what data my pycom node is picking up from my boat. Hey, so the rest of this video is going to be more proof of concept. Some of the things I've got to make sure work before I can actually start on the ourLora project is make sure that I can use that pycom low-pi 4 board, use micropython to send LoRaWAN data to the gateway. Also on the Things network, I need to try out the integrations. I haven't done that yet, but I want to use the HTTP integrations to send the data that it receives onto Firebase. And then on the Firebase side of things, I've got to make sure that I can write a cloud function that receives that data and puts it into the Firestore database. So here goes. So I'm using the low-pi 4 board from pycom. And the nice thing about that is it already has MicroPython installed on it, and also has additional functionality provided by pycom in their libraries installed on it for doing LoRaWAN. I'll be using the Things network to receive the LoRaWAN data, and I've put all this code into a repository called Payload, and that's out in GitHub. I'll add the link to the notes for this video, and this was really just to do proof of concept stuff, make sure I know how to use the low-pi 4 board, make sure I understand what its capabilities are, and create some library routines that I can use later on in my actual ourLora project. So ourLora project will be in the videos after this. So let's have a look at the code. So just like all MicroPython code, the code that's initially fired up is in the main py routine. So this is it here. As well, I've got two supporting files. One is called config.py. So this has config.py that has the EUI and the app key. Okay, so let's look at the main py routine. As I said, there's this low-pi helper, which is the main helper routines in there, and what it has inside it is a couple of classes to define the payloads that I'm going to be sending up to the TTN LoRa gateway, and also has some supporting routines like blink to blink the LED on the device in different ways to indicate where it is, what it's doing. It's got a routine to set the frequency plan. This needs to be done for US, and we'll have a look at that. Also got a routine to join the LoRaWAN and TTN network sessions, and also got a routine to send data. So if we go through the code here, so the first thing that happens after startup is it turns off the heartbeat LED. I want to get the EUI of the device that's on the device, and this routine here will print the EUI, and that's useful when setting up the device on TTN network. It needs to know what the device ID is so that it can make sure it's receiving data from a particular device and sending it to the application. Down here, when I'm in production, I comment out this if true line and change it to if machine reset cause equals deep sleep reset. So in most cases, it's going to be looking for the code coming back from a deep sleep. If it's coming back from a deep sleep, then it goes through, sets up a LoRa object, just a basic one. It does a restore of the last LoRa session from non-volatile RAM. If it finds that a session is there, it has joined, then it'll print that it's using that existing session, so it doesn't have to rejoin. Else, if it finds it hasn't got a join session, then it will actually do a LoRa join and call the join routine that's out here in the LoRa helper. The other choice here is, again, in production, if we haven't come into here from deep sleep, so really just the first time we're coming into this main routine after, say, a power on or a reset, then it just does the join, same join as up here, to create a new LoRa session. These joins can take a little bit of time. Usually they just take 1 or 2 seconds, but I've seen them take up to about 60 seconds. So that's the reason that when I'm in development mode, I just want to use the last session, so I just set it to true, because in most cases my non-volatile RAM has the last state of the last LoRa session in it, so this saves some time starting up. So once we've got a LoRa session, the next thing my routine does here is an example of sending data. Let me just start this in the meantime, so I'll just do an upload. So let's get started. You see here it's joined, it's sending data, and then if I go over to the TTN network, we see the join packet here, and then 2 data are being sent, and later on in this video I'll show you how I decode that data so I can actually read what the latitude, longitude, and the different sensor readings are on the different packets that are coming in. So we'll have a look here at this at the send. So we create a LoRa socket, and the other thing I have to do is say what data rate that socket is running at. So in here I've got the data rate set to 3, which is the fastest data rate supported by the frequency plan I've got set up. After that I create 2 objects, one for holding the sensor data and one for holding the GPS data, and we see how to set up these objects here. So they're based on these classes. So GPS payload, it holds a latitude and longitude variable on init, so that's what I'm calling when I first initialize an object out of this class. I'm passing the longitude and latitude, and it's setting these 2 variables inside the object to the whatever I passed in there. And then the 2 other functions that are supported in this class is the pack one, so it uses a Python structure library to pack the contents of the class variables, the longitude and latitude, and it uses a pack format. So FF means two floating point values are going to be packed as binary data and returned, and it also has a routine in there to calculate the size of that packed data. And you see here I've also got the same thing, but a class for the sensor data. And where this is being used after I've created those two objects is I do the two sends here. So I'm calling send, and what it needs as parameter is the LoRa session, the LoRa socket that I'm using, which I set up here, the port that this should be sent to on the back end, what class of payload is being sent. So in this case I'm sending GPS data, on the next send I'm sending sensor data, and whether ADR is being used. So again, let's have a look at the send routine that's in LoRa helper. So here we see the send. So the send routine is actually doing a quick blink of the LED, so I know it's sending data. It sets the sockets blocking to true, which means when the socket actually sends, it won't perform the next line in the code until that send is complete. I set the port for the socket, which came from up here, and the port is the indicator of what type of payload it is. I've just got a print command so I can see what I'm sending, and you can see down here in the terminal what the printer's actually printing out, so the binary version of what's in that payload and the size of the payload. So you see here's one for the two floating point longitude and latitudes, and here's one for the packed sensor information. So I'm keeping these really short, less than a size of 11, and that gives me a lot more choices to what data rate I'm using. So after doing the send, I just do a sleep to make sure everything's complete. I turn the blocking back to false, and I also do this LoRa session save. So it's saving the current LoRa session information to non-volatile RAM. And we saw before, when this code in main first starts up, if we're either coming back in after a deep sleep or I've just got it forced to true, then it's going to restore the information from that non-volatile RAM and use the existing session and save time. And the last thing we can see here after doing the two sends is I show going into a deep sleep. So in this case I'm sleeping for 60 seconds, but on a real IoT device you might sleep for an hour, for a day, and then we come back around and start again. So we see the data's been being sent since I started this, and if we look at our TTN network, we see all that data coming in. We're sleeping at the moment. If I hit reset on the board, you see it's restarting here, and because I've set up for it to use the existing information, the non-volatile memory version of the session, it just used the existing join and started straight away sending the data. I think one other thing to look at here is in this LoPi helper, the actual join code is in here. So this is where it does the full join, and it waits in a loop while it's joining. The interesting thing here is this is where it sets the US frequency plan for the session, and here's the routine for doing that. So I found for these pycom devices the US frequency plan wasn't well set up, so I reset it up by basically clearing out all the channels that were already set up. So going through from channel 0 to 72, which are all the ones preset for the US 915 frequency plan, just clear out each of those channels. And then for the TTN network, it's really only using or looking for 8 transmit channels. So I'm just doing an add channel with this information for each channel here, and I print out the results of the add channel here. All those channels being set. So data's been sent to the Things network, and it's been sent in these binary formats. So port 0, BE9A, which is my longitude and latitude, and also on port 2, this format E902, which doesn't mean much as a binary. So let's go over to our Things network, and we see the data coming in. So we see these BE9A, E9, the data coming in. We see that the port is recognized, and it's being translated into the real values here. So this is done in the TTN network through setting up the payload format. So let's go into here. So payload formats uses JavaScript code to extract real readable versions of the data from the binary format coming in. So I'm using this decoder here, and it's receiving the bytes and the port number. So that's why port number is important. It has a couple of subroutines in it, so bytes to float and bytes to signed int, a couple of routines that I'm using. And then if it's port 1, which remember is our longitude and latitude, it just returns longitude, or an object that contains longitude, using the bytes to float routine up above. And just looking at the first 4 bytes of that data packet coming in, and then latitude is the second 4 bytes of that data packet coming in. So just doing the translation bytes to float. And similar sort of thing for if it's port 2, which is our sensor data. So it breaks up the byte data into the 4 bytes. So Celsius using the byte to signed int routine, because that's a signed value that's coming in for Celsius, so it can measure negative temperatures. For humidity and water level, I didn't need negatives, so I just used the full 256 possible values for humidity and water level, which humidity is a percentage, water level's number of centimeters. And then for voltage, that comes in as again 256 discrete values, but I divide that by 10, so I get a voltage reading from basically 0 to 25.6 by dividing by 10. So this can tell me a battery, like a lead acid battery voltage level. So that's Finally, I wanted to put a proof of concept together about how to get the data from the TTN network into my application, ourLora application, which will be running in the Google Cloud. So for this I use integration. So again, under my application in the TTN network console, I go to integrations. So I want to add an integration. There's some built-in ones here, but I'm going to use HTTP integration. Basically have to give it a name, so let's call this one access code. What it'll put into the response to allow me to send messages down to the device. I'm not actually using that. We need to put in a URL. So in my case, it's probably going to be ourLora.com TTN. Then I'm going to use a post to send the information up to my server that's receiving this. You can also add authentication headers, custom headers, so you can help uniquely identify the packet coming into your host service to make sure you're not getting spurious ones that you didn't expect. So when I do this for real, I'll set these things up just for security. Then I click on add integration. So at that point, any message that's coming in to my application will be sent on to this HTTP endpoint. And I test this out using my LupinPet tool. Again, it's up in the LupinCorp website. You could also use Wireshark, but basically I set up a dummy web server at the location that I put in the integrations. Because it is a dummy, it only send back 501s to the application, but at least I'll still see the data come through. So this is on this 5th packet. You see an example of the data that comes in. So I copy and paste that into a bigger view here. So this is what it looked like at host ourLora. So just the normal HTTP headers, and then all this information that's in that packet being sent from or being received by the TTN network and sent on to my application. So some of the things that I'm interested in is the metadata about the time. So this is what I can use to timestamp the data coming in from my IoT device. The payload field, so this is an example, so here's the raw data, but I'll be using the payload fields that have been decoded from my payload. It makes it easier to work with, so these I'll grab over in the Firebase cloud function, pull it out and add that data into my Firestore database. There's other information here. I don't think I would really use any of this other ones for things I'm doing, but you can see there's interesting information about what frequency that data came in, what data rate it's running at, all sorts of good information you could use. And that's about it. So I think this is my proof of concept done. I know what the data is going to look like coming in on the Firebase side of things, so I can write a cloud function to process that, and all that will be in the later ourLora specific videos that I'm putting together.